The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com. Hello and welcome back to the Ben Heck Show. It's that time of the year again, holiday season. What sort of cool build should we make for it?
When you were a kid, did you ever try to sneak under the tree and peek at your presents to see what you got?
Yeah, it's hard to remember that many years ago, but I'm pretty sure I did that.
Toys always had that nice plastic rattle. So what if there was a way to detect whether a present was removed from under the tree?
Oh, okay, yeah, like a tree force field. Probably the easiest way to do it would be with weight.
Yes.
We could buy some cheap digital postal scales, remove the weight sensors from them, and then build 3 of those around a circular base.
Okay.
A microcontroller could constantly monitor the weight values, and then if there's a change, either more weight or less weight, sound an alarm. And we could add a key. When you turn the key, you can kind of reset it. So if the parent wants to change something under the tree, they can turn off the alarm and then, turn it back on once they're done.
Oh, and you know what? We could use one of those tree skirts to kind of conceal it so that it's stealthy, so that you don't actually know that there's a sensor under there. Oh, this could also be useful for keeping pets away from the tree.
Hey, that sounds great. All right, I'm gonna find some digital scales to take apart. Let's get started.
Amazing hacks.
How can we make this portable?
Inspired designs.
I am the internet troll.
Regrettable acting.
Batten down the hatches!
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
So Felix, we need to figure out a way to sense changes on the present platform. I was thinking cheap digital scales.
How about we tear it apart?
Yeah.
Don't turn it on.
Well, I kind of thought I could try to punch it like in Rocky IV and see how strong I was. I'm not as strong as that guy in Rocky IV though.
Mr. Drago?
Yeah, you remember he was punching computers and it was 1,500 pounds per square inch.
Yeah, he's a tough guy.
So this scale can do up to 50 pounds, which means if we have 2 of them, we can go up to 100 pounds, 3 would go to 150, so you could almost put an entire person on there. Oh shoot, I cut the foil, now my warranty is void on my $15 scale. Yeah. Darn it.
I think this is kind of an interesting project because I've sort of been curious about the strain gauge because a friend of mine had a weight scale that broke and wanted me to fix it. And I took it apart and I found some interesting thing inside of it and I didn't really know what it was.
Oh, there's buttons on the side? What do they do?
They hold.
Oh, okay. We're not after the electronics, we're just after the element that senses the weight. And we're getting pretty close to it here.
There's not a lot in here, but this is very interesting.
The screwdriver that eats like a meal. There it is. So this is the strain gauge. This part is attached to the base of the scale, and this part hangs out in space and is connected to the actual thing that you are measuring the weight of. And these wires here basically detect very small changes in the metal, and that is calculated into a weight. So you did some more research on this, right? Mm-hmm. It's called a Wheatstone bridge?
Yep, there's 4 resistances, and as the metal deforms, it causes a subtle change in the resistance. And 2 of those leads, there's 4 leads on here, and 2 of them, a small voltage is applied, which causes a magnetic field, and then as the magnetic field changes, it induces a voltage.
So then by detecting that voltage, you can tell how much the metal has been deformed.
Yeah, and there's a way to calibrate it so you know how much, you go with a known weight, and then measuring the difference with the known weight and the change in the voltage, you can calibrate it to get the right accurate measurements.
Okay. Well, I don't think we really need to do that because we just need to look at a set weight, like what the presents weigh, and then look for changes. Basically, 2 of these are excitation to start getting a value, and the other 2 are to sample the value. All right, let's hook up an op amp to this to see if we can get some measurements. Okay, we've hooked up an operational amplifier to the Wheatstone bridge. And what that does is it takes a very small change and amplifies it. We did that before with the Puppet.
Oh yeah,
that talked
yeah.
automatically. the very small waveforms that excite a microphone via your voice, you have to amplify them quite a bit to actually be able to do anything with them. The signals are actually very low. And that's what we're doing with this here. So we've just hooked the op amp up to the analog in, or the ADC of an Arduino, just to get some numbers off of it so we can see a change. Again, always start slow with like a very, very simple example and make sure that works before you add more complexity to your project. All right, so we're getting, well, I would want to say around 0. Let's apply some pressure. Okay, yep, the number's going up. Just like Ivan Drago, I'm gonna punch it and see how many pounds of pressure I can apply. Ugh. Yeah, that's the real trick, is how constant it is, you know? Because we don't actually have to know what the weight is, we just have to know that the weight changed. Originally, we properly calibrated each scale to get the accurate weight, in this case, 0.1 pounds. But then we realized when the scale was uncalibrated, we actually got a lot more sensitivity. For instance, this piece that weighed 0.1 pounds shows up as 5.1 pounds, which makes it 50 times as sensitive to weight changes. Okay, we're back to having the uncalibrated version of the chip. It's reading 0 pounds. If we go up, we actually get a negative measurement. That's fine. But yeah, let me try blowing on it. Wow, look at that, 0.3 pounds.
Yes, 0.3 pounds.
That's a lot more sensitive. Hey, grab that piece of cardboard.
There you go.
Put it on there. Hey, look at that. We can see this little piece of cardboard. So that's right, little Billy and little Susie. If you try to even get a piece of cardboard on the Christmas tree, you're in for it. So the proper calibration was negative 35,000. The default was negative 7,000. So we knocked it down to negative 100 to see how sensitive we can get it. Try that piece of cardboard now, which was 0.3 before. Whoa, that thing weighs 5 pounds now.
Yes, 5 pounds, 5 whole pounds.
Check it out, I'm applying 6,000 pounds of pressure with my fingers.
Holy cow.
He is like a piece of iron. Okay, what do we got? We have, let's see, average, would you say? 0.5 to negative 2. Oh, that's positive 4. So I'm thinking we figure out what the average is, and then we look for anything within a pound of that. So like negative 0.5 or positive 0.5 over, and that triggers the alarm. Otherwise, yeah, just probably even, yeah, waving your hand around. See how the air density changes?
So sensitive.
That's pretty cool. You know, if you had 3 of these, you could use it to detect aliens, like on a ship, if you were Sigourney Weaver.
Oh yeah, you can detect movement.
Yeah, because the guy's like, oh, it works off micro changes in air density. Let's measure the actual weight of this, just to see how sensitive it is.
Here we go.
Wait for it. Okay.
0.2 ounces.
Wow, that's not much at all. So 0.2 ounces here becomes 4 pounds. Yeah. So yeah, that is several orders of magnitude of sensitivity. Great. So we just have to make sure it's not too sensitive so that air changes don't cause it to trigger. But then yeah, if you go over 1 pound of uncalibrated change, boom, the alarms go off.
So we have figured out how to get all 3 of the sensors to read through these load cell amps into the microcontroller. And the next thing that I'm going to do is take the load cells and attach them to lengths of wire. On one side will be the load cell and the other side will be this plug. And then we'll take the plug and we'll have receptacles on this board here. These receptacles will connect to these 2 load amp cells on here. They're load cell amps on here. And then we'll port that out to the microcontroller. And this will fit into the box that Ben is designing. The load sensor requires 4 signals. We're using an old USB cable, which is perfect, plus it's shielded.
While Felix is wiring up the multiple load cells, I'm going to get started on the enclosure for the key lock. So I grabbed this off of an old arcade machine that I saw sitting at the curb at our old shop, and I'm finally using it. Yeah, recycling. So I'm thinking that when the key is out, it will be in the armed position. Then when you put the key in and turn it, it will disable the system, so any changes you make to the weight won't set off an alarm. And then when you turn the system back to armed, it will set the new current weight as the default. So if you remove a present or add a present, if you're the parent, this is basically the tare. This is how you reset the weight of the scale. So I drew in the lock into Fusion 360 here. So I drew the nut, and then I drew a little piece on the end, and this is what will turn when you turn the key. And I'm thinking we'll have the switch like this, right? So when you turn it, it will disengage the switch, and then when you turn it, it will engage the switch. That's how it knows that it is on. Okay, so if we go back from there, there's also going to be a body like this. It will have a power input hole right here. We'll probably just use the existing wall warts from the scales. And then in the back, we have 3 openings here for the 3 plugs going to the sensors. And then one final hole that will be used to output to a speaker, which we'll probably have outside of this box. It'll be somewhere else. I might make a separate enclosure for it. Yeah, and then also inside, oh, that's the lid. Inside there'll be a little mount right there, and that is where the switch goes. All right, let's get printing. Okay, so here's the case that we printed. So there's the arm switch. Okay, I've converted the library over to the PIC32 dev board that we use. I've also made a few changes. There were a few things missing. There are 2 sensors in each one of these circuits, but the second sensor wasn't really written into the code, so I had to add a few things. Basically, there's an A channel with either 128 or 64 gain, and a B channel set to a constant gain of 32. So if we use both channels in one device, we actually have to scale them to make up for the fact that they have different gain, even though they're using the same sensor. All right, so let's flash the code over. And I've got the 3 pieces here on the desk that I can use for an example. I've got 3 pinballs of equal weight, and then this heat sink, which has a little bit of weight, but is still very light. This could be like a single holiday card. Okay, let's look at the numbers here. So when this thing first turns on, it gets like a baseline reading of 10 samples from each of the load cells, and then it offsets all future readings by that. So if it's actually like negative 83,000, it offsets that every time to give us something closer to 0. So here are the 3 numbers coming across the screen. Yeah, they're not exactly the same, but that's all right. So I'm gonna set this, actually let's set the pinball first because that's a lot heavier. As long as we're in the same ballpark, I think we'll be okay. All right, yeah, we're right around 800 for that. Take the pinballs off. Okay, so here is a very light heatsink. Let's use the center one, which is averaging about 20. Okay, it jumps up to about 98 or 100. So that's about 80 difference. That's quite a bit. I mean, if you put any amount of pressure on it with my hand, look at that, we're jumping up to like 20,000. Not even Ivan Drago is that strong. Yep, that's right, more Rocky IV references in this episode. So even though these 3 sensors aren't giving us the same reading for a multitude of reasons, the difference is consistent. If I put this little heat sink on any one of them, we get about 80 in difference. So that's perfectly fine. So I would say I'd probably make it so if there's a change of more than 50, it triggers the alarm. So here's how the key works. If you want to change a present or add a present, you stick in the key and you turn it, and the display will go to tare. Of course, you won't see this, but it'll be happening inside. Then you add whatever you're gonna add, and then you take the key out, and that will be the new default setting. So the key basically changes the default and prevents the alarm. But then if any of these change, one way or the other, up or down, the alarm will go off. Let's go over this one more time before I build it into the frame. Got the power supply. Power supply connects to the microcontroller. Microcontroller has a transistor to drive the speaker. There are 2 sensors in here, and connections for the load cells, which are out here, and enough wire to spread it around the base of the tree. So I'm going to pack this up and then we can build it into the base. I'm using the CNC machine to cut the top and bottom pieces out of MDF. The top is in 3 pieces, which will hinge together, giving it a little bit more sensitivity. The bottom has a large cutout for the Christmas tree stand itself, plus 3 slits for the load sensors to sit in. I then wire everything up using the cables that Felix made, and finally attach a felt Christmas tree skirt, making sure the felt doesn't interfere with the sensors. I've hot glued and modified a tree skirt to our pressure sensitive base. Let's do a few more tests. I'm gonna plug it in. So when you first turn it on, it will check the tare or the, 0 weight, and then it will just continue to monitor it. And if you turn the key, it sets it to reset weight state. So if you put things on it, that will create a new profile, so to speak. It's really just 3 variables. Turn it back, and it's armed. So it's the weight changing, either up or down. So if I remove something, it'll also go off. Oh yeah, we can try an Indiana Jones scenario. Let's get one of these gift boxes. Dun, 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 dun. Smugly walk away. Give me the whip. Oh, I guess they're close enough to the same weight. Come on, Indiana Jones had a bag of sand, and that was half the size of a golden idol. I thought that guy went to college. Okay, I've got the tree all set up, and if anyone comes near it, I'll know. Well, no one's gonna mess with this tree thanks to the Holiday Present Protection System. Well, Karen, we finished the Holiday Present Protection System.
All right. Do you think we met the challenge?
Yes, it definitely sets off an alarm if you do anything near it. In fact, it's probably a little too sensitive.
Okay, so were you pleased with the outcome?
Yeah, I was. We bought the cheapest scales we could possibly find, and I was worried they wouldn't be sensitive enough. But it turns out you can actually get a lot more sensitivity out of them than you even normally do with their pounds and ounces.
Do you think that was because of the combination of using 3 scales at once?
Well, I think it's because the sensors just have a lot more sensitivity than they really need for pounds and ounces. I mean, there's a lot more division than, 1 pound might be, 200 units on the device. So you can divide that a lot further than just into 16ths to get an ounce. I mean, it would probably obviously show more accuracy if you were using the metric system.
Yeah.
Because you're talking about thousands of something rather than a 16th or a yard or a stone or a drachma.
So if you're going to do something differently on this build, is there anything you would have done differently?
Well, we should have put in a potentiometer to adjust the sensitivity.
Okay.
We had it going off, like an envelope being set on it would cause it to go off, which is probably a little too severe.
That's really sensitive.
Well, we were noticing when we were filming the reveal, like just the vibrations on the floor, stepping around it, even with a concrete floor, was causing it to go off.
And if you're using a real Christmas tree, those needles falling could even set that off, maybe.
Yeah, maybe not a few needles, but definitely a week's worth of sheddage or whatever, like if someone forgets to water it.
I never did that as a child. I always watered it every day, stabbing myself in the face with pine needles.
Did it make you feel like you were working on a car, like,
A little bit. Or like a little Mission Impossible, like trying to sneak in there without stabbing myself in the face.
That's true. If you wanted to put your top secret files in that tree, Tom Cruise, I don't think he'd be able to get it.
Oh, not without setting off that alarm.
Yeah.
And even if you tried to send his cat in, it still gets set off.
And even if you breathe, Ethan Hunt, it'll detect it. How will you not breathe? Simple, I won't breathe. Dun, 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 dun.
So, have you ever built any cool, interesting holiday mods or gadgets? Let us know on element14.com/TBHS.
where you can also read about our upcoming builds, special events, and episodes. Also, don't forget, if you have any cool build ideas for us to do on the show, send them in to Karen via social media, and we'll talk about the 5 best entries per month. We'll see you next time.
It needs to be farther in.
Can you read my mind? Like it's gonna make the world go back in time.
Come back down to reality, Mr. Heckendorn, please.
You were the one who started it.
Yes, and I'll finish it.
This is ancient Greeks argued about. Do you think there's a -0? You're a blasphemer, Archimedes.
Only if there's a number in between 0.
Take him outside the walls of the city and stone him.
Yes, let the 300 Persians kill him. The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.